inputs and the state of the flip-flops and so on. So the analysis procedure would basically involve obtaining the equations. It would also involve, well, obtaining the equations, and we talk about the equation, we're talking about the equations for the output and also the equations for the inputs to the flip-flops. We also want to get information about the state table, and then from that we can look at the state diagram, and that is how we really analyze. So it's really a reversed engineering procedure we are actually going through. When we design, we design from the other end. Now we are looking at, given the circuit, how do we say what the circuit is doing? And really it's a good place to start, because then you get a nice introduction to what is required to design these circuits. So as I said before, in the analysis procedure really is just to obtain the equations and then fill in the state table and so on. And then from that we can actually look at a state diagram. And so we are basically going to look at a couple of examples of how we can go through these steps or analysis procedure. So the first thing to ask here is, this is a look at this circuit, and let us just try and find out if it's first of all a clocked sequential circuit based on the information given in the figure or in the diagram. Would we say this is a clocked sequential circuit?
Yes, I would say, because the clock inputs to both of the D flip-flops has the input to it, so I would say the clock sequential circuit.
Okay, you're saying there's a clock input to the flip-flops, and that would make it a clocked circuit. What actually makes it into a sequential circuit?
So one of the flip-flops have to be feeding an input to each other?
No, well, as long as you have flip-flops, if you remember the general diagram for a sequential circuit is one in which you have a combinational circuit, and the combinational circuit is fed into a memory element or a memory storage. And the memory storage here will be performed by the flip-flops that we have. In this case, we are performing the memory storage with the D flip-flops. And we do have combinational circuits being fed into these particular devices, memory devices. So yes, this is a clock sequential circuit. And what type of memory do we have? We're just looking at the circuit, and I'm asking these questions. What type of memory do we have? By the way, that's a question.
Repeat the question, sir.
What type of memory do we have? In other words, this is the question here. What type of memory do we have?
Sir, is it a cache memory, sir?
Sir.
We are using cache, sir. You see cache anywhere on the diagram, sir? Remember, we're looking at this diagram in front of us here. Why would you say cache? I've never mentioned that word in this course. The memory type is a D flip-flop. It's right there in front of you. So we're using D flip-flop. What other type of memory could we use, if I may ask? What other type of memory could we use?
JK.
Yes, go ahead. Another one.
A T flip-flop, sir.
What?
Yes, sir.
T memory, sir.
Okay,
A
so
T flip-flop. Yes. Could we use
SR flip-flop, set reason.
So like him on join the class.
Sir, could it be a spram?
RAM, but RAM is just a method of storing. You have a device that actually makes up the RAM, and you have different ways that you make RAM.
So
So
set and reset is another one. Star flip flop.
fine, SR flip flop. But remember we are using SR flip flops in the configuration of D flip flops and so on. In other words, SR latches. Yes, we could use latch, but remember we said that latch, we don't use latch in synchronous circuits. For the
Yes,
main reason,
because of the
right?
memory level.
Right. So the memories are actually flip flops, which the main reason for that is that the transitions occur on the clock edge, the edge of the clock. So it occurs once during the cycle, clock cycle. All right. So these are D flip flops, and we identify that. How many state variables do we have?
Could be 2,
All right. Name them, please.
1 or 0.
Nah, those are the values. I'm saying variables based on the circuit.
A and B.
A and B. Okay, we have two flip flops. Each flip flop actually represents one state variable. And the value that may be stored in that particular state variable, 1 or 0. So A could be 1 or it could be 0. Similarly, B in this particular instance can be 1 or 0. So those are the two state variables. Let me just ask a side question. If we have two state variables, how many states do you think that we would have, could generate from these two state variables?
4.
4 states. How? How do you know that?
Truth table.
Based on the first two variable, you can add one if you have the A will give you 1 or 0, and the B
Okay.
can give you 1 or 0.
All right, fine. So we have two binary state variables, and therefore, if we put the two together, then we can have combinations, 4 different combinations for those state variables. And those will be states. All right, now what are the inputs? Let us see if we can come up with the inputs for these devices.
X.
Yes? What are the inputs? Did I get an answer?
X, sir.
X is the input, fine. What are the output?
Y.
So we have one output, one input. All right, so that's okay. Now, let's go a little further now. So once you have identified the input, so we're analyzing the circuit. So let's go ahead and analyze the circuit some more. What are the equations on the inputs of the flip-flop? In other words, let's look at the flip-flops and see what are the inputs to the flip-flop itself. First of all, let us do the flip-flop that is the state variable A. So that flip-flop,
So it would be A and with X,
continue.
plus, no? Yeah, plus X and with B.
All right, fine. So that's that. So I hope most of you would see that. A and with AX plus BX. And so that would be the input for the D input for A. What about the other one? What about the D input for the flip-flop that is controlling B?
That's
Not
not AX.
Not A.
X.
All right, fine. And as we can see now, so we have all of these plus the ones that we had before. We have generated the inputs to the flip-flop. But since we're using D flip-flops, we know that we want to identify the current states. Yes? What are the current states when we talk about D flip-flop? What would you associate with the current states for D flip-flop?
Sir, is it the previous state, sir?
Pardon me?
The previous state.
Previous state, and what is that, by the way?
Well, in terms of these flip-flops, sir, it would be not A and not B.
All right, let me ask you the question in another way. If you could touch the diagram, I suspect you can touch it on screen. I won't be able to see, but what point on the diagram, what place on the diagram would represent the current state? Where would the current state be coming from? Or the present state, whichever one you want to call it. Where would that be coming from?
Sir, the part that not B and not A is at
Not B and not A. You mean the
A complement.
the complemented output?
Yes, sir.
All right. So if you're saying the complemented output, why not just the uncomplemented or the true form of the output? Why wouldn't it be A or B for that matter?
So would the current be the data input that would be at the gate for A?
All right. If you just go back to the diagram, I don't know if you can go back to it in your head, but if you go back to the diagram that we looked at the last class, that diagram shows where the next state or the present state comes from, and where the next state comes from also. The next state comes from the combinational block, and it goes into the input of the memory element. So in essence, what you see on the presentation slide here now for A would be the input for the A variable, for the A state variable, that is DA, that would represent the next state for your flip-flop. So it goes at the input of the flip-flop. So that represents the next state. The output of your flip-flop, that is what is called the current state or the present state. So it's really just the output of the flip-flop that is called your current state. So if I should ask now, what is your current state? Then your current state is simply A and B. A coming from the flip-flop, the first flip-flop, the one on top, which is representing or producing the state variable A, and then B coming from the second flip-flop with the state variable B.
Okay, understood, sir.
What about as I just mentioned the next state? What is the next state equal to here? Or where is the next state variable? Where can that be found? All right, the next state, go ahead.
Where the for the A it would be where coming from the R gate to the D.
Right, so it's at the input of the flip-flop itself, yes? And then, so that value then would be the same thing as DA. You agree with that?
Yes, sir.
Fine. How about for B? What would the next state be?
Sir, input and DB, sir.
All right, so the next state will be equal to, so we're saying then that the next state would be equal to DA in the case of A, and it would be equal to DB in the case of B.
Sir, we kind of lost. I try to understand from when you say the current state. I try to understand how to get some kind of loss. Understanding, no, understanding. Can you just repeat it for me? Just so we can get pick up out of it or understand from it again.
I'm going to mark these values. Next state is at the input of the flip-flop right here. Right at the input. That's the next state. So let me write next state. Okay. Present state, the current state, present state is at the output. Just call it PS. I'm going further than that. Okay. So we are saying then, what is the next state value? In other words, what's the equation for the next state? And we are saying we have already calculated that DA is at the input of this particular flip-flop. So that's DA. It's at the input here. And DB is this one. So DA and DB represent inputs to the two flip-flops. Yes?
Yes, sir, I understand.
I'm saying now that DA actually is the next state equation.
Rita, turn on the microphone.
Sir, you can
I don't know who is that.
Rita, you can mute him.
Lord. All right, so yeah, we just mute Mr. Freighter. All right, so the DA is really the input of the input to the flip-flop. And so we said that the DA is the next state. So if we have an equation that specifies DA, then it also specifies the next state.
Sorry, my humble apology. I never realized that my mic was on. Sorry about that, gentlemen.
That's okay. All right, now as we move on a little further now. So by the way, is that understood?
The
Yes,
equation.
sir. I understand. Also.
All right, fine. All right, so we have now that, so we can go one step further and write the values of A and B, obviously, will be entered into the flip-flop at the next clock edge. And we all should know that. From the previous class, we went through that, and that basically should that should be clear. Now, if we go a little further, and let us see what we would calculate for the next state equation. So we can just write down the next state equation. If it's equal to B, if it's equal to DA and DB, then these are the next state equations. And therefore, you would have only Y to contemplate. What is the value of Y? And once we have the next state, we say that we're looking for input equations, next state equations, I want output equations, and so on. There's only one output if you look at the circuit, and that output is Y. And what is the value of Y? In other words, what's the equation that represents Y? What's the output equation for Y? And by the way, that's a question you could also
B
answer.
or B or A and X X complement.
X prime. All right, fine. So that's quite fine. So that's the equation for y, the output. So the next thing, once we have those equations, we can now move to the state table, and we can represent all the different values now within the state table. So we have the present state values together with the, let's go back to the circuit now so that you understand exactly what it's talking about. We have the present state values together with the input values. And we now want to find out what are the next state values and the output values that will be generated from those. And so that is what we call the state table. Okay? So if we put that information, if we use all the equations that we have, all the equations of the different inputs and present and current states, then we should end up with a table that shows everything. Now, because we have three inputs or three input variables, we have the two state variables and we have the input variable, the external input variable, that is the input that is coming from outside of the circuit. We have three variables, and therefore we have 2 to the 3 different combinations. So we have 8 different combinations for those 3 variables. And obviously we know that we go from 0, 0 all the way down to 1, 1. Yes? Now we're 0, 0, 0 and to 1, 1, 1. Now, if we put all of these values into the different equations, then we should end up with our next state variables and our output variables. Now, let us see. I want you to check for yourself just to verify, giving you about 2 minutes because I won't go through each of these one. But just verify for yourself that this table is indeed representing the equation, set of equations that we have right here. I'm giving you about, let us say, a minute also to verify. Are we okay in verifying the table?
Yes, yes, going.
It works?
Sir, I have one question, sir.
Go ahead, please.
Sir, for the part for the B next state, sir. The first one that is under B and the next state that
You
coincides
mean
with.
this one here? Is it this one?
I'm not seeing a pointer, sir.
All right, let me. Is that?
No, the one, as in the value one itself below that.
The one beneath this one? This here?
So you just circulate, yeah, that one, sir. All right, that coincides with the equation, sir. But the other value of one, we are going to have B
value.
under the same B line, sir, the second value of one. which is at the fourth
This
row.
one there.
Yes, sir.
Okay.
I don't see where it coincides with the equation because it says B is high in the present state and X is high. I don't see where that coincides with not A.
You don't see where
It doesn't have to do with B, only A and X.
Remember, you're using the present state to find the next state, you know. So the present state of A would be 0, and then not A would be 1, and the input X, which is 1, and that's how you get the B value right there.
So I'm guessing it's a case where it doesn't matter the value of B, it just only matter the value of A and X.
look at the equation for it, the next state equation. All the equations are there. So I'm telling you, if you see the equation, all the values that you get from the truth table must correspond with the same next state equation. So all the next state values must correspond with the next state equation. These are the equations that generate the values within the truth table for the next state. So you have two next state equations, one for A and then one for B. So you're looking at the B values. So therefore you should use the next state equation for B to calculate the values, the next state values for B.
Okay, sir.
And if you look at that equation, obviously it doesn't have anything at all to do with B.
So it doesn't matter what B is.
Look at the equation. Can you see the equation?
Yes, sir.
What does it say?
Not AX.
Right. So it says this is the next state. If you didn't know that's saying the next state of B.
Yes, sir. I understand that.
And this is how you get the next state. You don't see anything that has anything to do with B inside there, right?
Okay, all right, sir.
Kind of hard to follow. Maybe it's because I joined the class late. Kind of they run out of data plans, so I had to go and buy some credit. But not really following, even though I'm trying to catch on.
It is going to be there because this has to do with, I was explaining. All right, I understand, but I'm saying this must be done. You're gonna have to review the video or the recording to see if you can get some of the information that was done before. Also, it doesn't have to do with only this particular class. We are relying on stuff that we learned last week. We're also relying on those stuff.
Okay, sir.
All right, so once you have verified that we're okay, this table is concerned, let us move on to another form of the table. Now, we could also look at the table in another form or format. And this second format here is really a compressed format. And you would find you may want to switch between the two formats depending on the question itself. And therefore, it is good to know how to maneuver between the two formats. Now, if you look at this, we have also given, if you look at the second format here, the next state values are paired based on the value of X. So in one case where X is 0 and in the other case where X is 1, and so are the outputs. You could basically do that. And you would not suffer so much in terms of the amount of rows and columns. You would actually have a reduced number of rows, but on the columns, you probably would end up with 1 or 2 more columns. But it usually is, well, it's lighter on the eyes, and you can actually, if you understand how to get it, then fine. But as I said before, it is always good to know these two different formats because you can, depending on the question that you want to do, and one makes things a little easier than the other from time to time, depending on the question. So you need also to verify again that this is actually the same. And let us move on after you have verified the second form. We're saying the same thing as, is it saying the same thing as the first?
Yes, sir. It is saying the same thing, sir.
All right. Are there any problems with the second format? Do we have any problems with it?
No, sir, good.
All right. So I suspect we are all fine. Now from the state table, the next thing we want to look at is the state diagram. Now the state diagram, as you should know, is really just a diagram with certain symbols. Some symbols represent state, and we have other symbols representing edges or arcs, as some people would want to call it. And edges together with the circles and state symbols and so on would show all the different transitions from present state to next state, and also what are the inputs and the outputs for this particular circuit. So let us look at the state diagram for this particular circuit. And here is just a graphical view of the state table. So the circles, as you should know, are representing the states, and in this instance we have 4 states. And the 4 states are actually the combined values of the state variables. And now let us look at just the setup of these particular state diagram. The arcs are usually called edges. So in other words, the arrow lines are edges, and they're also called arcs, and they are the transition from state to state. So the arrowhead is important because it tells you where you're starting and where you're ending, and therefore it tells you the direction of the transitions. Now, if you look at this particular state diagram, the arc or the edge is labeled with both input and output values. Okay? Not all state diagrams do this, only some. All right? In this instance, we are showing the input and the output on the arc. The state is within the circle, and the arrow again shows the transitions for the different input values. So we look at each input together with the present state, in other words, the current state, the state that it is at. The system is at a particular state, and when it gets a particular input, what is supposed to happen? Where is the transition? Where does it transition to? And what is the output? And so on. So in this particular instance, let us start with 0, 0, that particular state. So if the present state is 0, 0, we are supposed to transition to a particular state depending on the input. Now, if the input is a 0, where do we transition to? If you notice, the arrowhead or the edge really leaves from the 0, 0 state and it comes right back to the 0, 0 state. So it means that we remain in the same state. The output at that point is simply 0. Now, again, I want you to, well, let me just do one more. If we get a 1 at the 0, 0 state, then where do we transition to? Well, based on the edge or the arc, we look at arc with a 1 on the input, which is this one here. Let me identify it for you. So this is the 1 on the input. So this here is the 1 on the input. See, I've underlined it. So that's a 1. So when you get a 1, you transition to state 0, 1. So 0 for A, 1 for B. And then the output is also 0.
I'm not seeing where you're underlining things, sir.
You're not seeing it on the screen?
No, sir.
Is anyone else having the same problem?
No, sir, we're seeing it.
You're seeing it?
Yes, sir.
Yes,
All
sir.
right,
I'm
okay.
seeing it, sir.
All right, so if it is that you're seeing, if you're not seeing it, I wouldn't be able to tell you what to do at this point. Again, the normal thing is to refresh and then try to see if that works. And if it don't work, then the other thing is to try to re-enter the conference. So you log out and log back in. All right, so the transition from once we are at 0, 0, in other words, A0, B0, and we get a 1, then we transition to the state 0, 1. So A remains 0, but B now is 1. And then the output is also a 0, and that is what this says. So what I wanted to do now is to look at the state diagram together with the state table to see if it is they are corresponding and both are doing the same things. In doing that, you will get a little bit more understanding of the state table and at the same time the state diagram. So I give you another minute.
Sir,
Go ahead.
question, sir. When the input is 1, sir, and it transition to the 0, 1, you were saying something about the input, sir, and I didn't get that. Where would the output? I mean, where would the output be shown, sir?
This is the output. The output, if you look here, it says sometimes we label the input and the output on the arc or the transition
Oh,
around
okay,
the edge. So
okay.
it's input together with output. So this 0 here represents the output. Yes?
Okay.
Question,
All right.
question, sir. That mean the values in the circle would be the present state, right?
Yes.
Okay.
It's really just the state, not just the present state. It's state because you will transition between them. It's the 4 possible state that the circuit could be in. I don't want you to call it a present state because it's also the next state to some other state. Okay?
Yes, sir.
So they are really just states.
Sir, or you could say simply put the state where when you're following the arrow, where the arrowhead is, that is the next, and the one it's coming from would be the present.
I don't want
In
you to
that
do that.
instance.
I really don't want you to do that yesterday either. Just
Okay.
think about them as states. And
Right,
you
sir.
transition between the states depending on the inputs that you get. Remember,
Okay.
the state diagram here does a whole lot of things. Remember, if you remember, the input, the output of the circuit depends on the present state and also on the input. Yes?
Yes, sir.
That's basically the difference between a sequential circuit and a combinational circuit. So that the output depends on not just the input, but it depends on also the present state. And similarly, the next state depends on the present state and also the input. So therefore, the state diagram is actually showing you everything. It is showing the dependency between the input and the present state for both the output and the next state. So the output if you can identify where's the output being displayed, then you can identify each of the output for each input and the transition that goes along with it, and so on. So the state diagram is actually showing every single thing, how the states are related to the input and the output for both next state and the output itself. All right. So I wanted to, as I said before, just take your time and go through this and look on it. Let me look at one more. Let us say we are in state 1,1, and I'm going to circle it here. So that is the state. While in state 1,1, I can get a value of x, or x equal 1, or I can get a value of x equals 0, because x is the only input that I have. What happens in the case where I get x equal 1?
So when x equal 1, so it goes to the next state of 1, of a being 1 and b being 0.
When x equal 1, when I get the input value for x equal 1, it goes to 1, 0, state 1,
Yes,
0.
sir. With the output of 0.
Fine. How about the other value of x while I'm at state 1, 1?
So it
Can
goes
anybody
to,
else tell me about that one?
okay.
I want someone else to tell.
It goes back to 0, 0.
It goes back to 0, 0. And?
The output is 1.
All right, so that's the full description. What about when it is at 1, 0?
It repeats with an input of 1.
What do you mean by repeat?
As in 1, 0 will become 1, 0 again with an input of 1.
So you never really specify the input, sir. That's why.
Yeah, don't change in the next state. Only
All right.
thing we change is the input, is the output.
So I want, when you're describing, you see, you need to get this thing here systematic. You're describing what happens, so you simply tell me what the next state is and what the output is.
Okay, sir. So when the input is 1, the next state is it remains the same, sir. And when the input is, and the output would be 0, and when the input is 0, the next state would be 0, 0 with the output of 1.
All right, fine. All right, so this is basically how you would analyze a circuit, a sequential circuit, a clocked one. And again, that analysis really is different from the combinational analysis, because if you remember how to analyze a combinational circuit, you look at Boolean equations, which are equations between relationship between input and output, and you fill in a truth table. What you fill in here is a state table, okay, and the inputs and the outputs again are not just related to themselves, but also you have to take into account the state of the circuit itself. All right, let's look at another example. And this example now, we're going to look at one where the output really and truly comes from just the current state. In other words, we don't have an output for y as we did before. The output really just comes from the current state. In this particular instance, can we identify going through the same procedure, can we identify the inputs? How many inputs do we have? And it is there. We have 2 inputs, x and y. Just look at the diagram and you will see everything that we want, x and y. We have one state variable, and that is a. And we are also working with a D type flip-flop. That's the memory element that we have in the circuit here. All right, so if we have one state variables, how many state do you expect that we should have? That's a question, by the way. Two. All right, well done. Now, how do we go about obtaining what is the next state equation and the state table and the state diagram? We need to obtain those as we did before. What is the next state equation? If I ask you that, you should know where on the diagram next state. Where is the next state on the diagram? So that you can obtain the equation at that point.
XR
Y.
AXR X or
R. XRA.
All right, so I hear a whole lot of different things, and it sounds as if you're heading towards the correct thing, but then I'm not hearing everything all at once. So somebody just tell me what is the equation for
AX
the next
or
state.
X or Y.
Say that again.
AX or X or Y.
Okay, so it's really just a 3-input XOR gate. That's what that is basically what the next state equation is. And yes, it is. So the next state is A XOR X XOR Y. So it's the exclusive OR of the present state together with the two inputs, and that will give you your next state. Now, what about the table? Let us look at this table, and I'm going to give you the table, and then you look at it now and tell me if it is that this table is okay. So tell me, I'll give you a couple of minutes to verify that it's okay. Well, not a couple, but when I say a couple, I really mean 1 minute in this instance. So can you verify that this table is representative of the circuit that we have, the state table here?
Yes, sir.
Yes?
Yes, sir.
Yes, sir.
All right. As you all should know, let me tell you that easy. For those of you having problems recognizing whether or not it is correct, remember the table has 3 inputs. Remember the present state is also an input. Yes, to the circuit itself. It's an internal input. Nevertheless, it's an input just the same. We have 2 external inputs, which come from outside the circuit in the form of X and Y. So we have these 3 input variables, and therefore to generate again 8 different combinations of these 3 input variables, binary variables. Now, in the case where we XOR all 3 variables, now we're to find the exclusive OR of it. It's really just finding the XOR gate is really an odd function gate. In other words, it simply identifies the inputs or the number of ones in the inputs. And if you have an odd number of 1, then it gives a 1 at the output. If you have an even number of 1s, it gives a 0 at the output. And that is how the XOR gate behaves. So if you can go across the 3 variables and just identify where you have an odd number of 1s present in the 3 input, then you can identify where you would have a 1 at the output. And so you could go through that quickly. So we have an odd number of 1 here in this row. We have an odd number of 1 in the next row here. All of that. An even number of 1 follows, and this is an odd number, this is an even number, this is another even number, and then this is an odd number of 1s. So those are the places that you would see a 1, or you get a 1. The state table, the state diagram, sorry, obviously you are expecting, as I said before, you are expecting 2 states, and you are correct in saying 2 states, because we only have 1 state variable. It's a binary state variable, and therefore we end up with 2 states. Now verify again for yourselves that you understand what the state diagram is saying. And I'm expecting that, well, let me not say. Verify for yourself that the state diagram is actually saying, and ask questions wherever you have a question to ask.
Excuse me, sir.
Go ahead.
It's a question relating to the arc, and you're saying that the leftmost digit represents the input, correct?
Yes.
And the rightmost digit, or binary digit, represents the output.
No, that's not in this case. And so that is why I'm asking you to look at it to see if you understand what it's saying.
Okay,
It's not,
sir.
not in this case. If you notice, we are using a comma now.
Yes, sir.
This particular diagram is only showing
Inputs, yes, sir.
Okay, so it is basically saying when you have 0, 0 and 1, 1,
It's the same thing.
you get the same thing here.
When they move from
So either 0, 0 or 1, 1 is the same behavior. And then 0, 1 and 1, 0, depending on where you are, it's another behavior. The transitions like when you get either 0, 1 or 1, 0. So that's basically what you're saying. And
Yes,
since the output is really the current state, we really don't have to go and do. We could actually represent the output by itself, but the output, you're actually looking at the output when you look at the state. If you understand what I'm saying. So you don't need a separate notation to denote your output, because you're looking at the output is actually at the state. Whatever state it is in, then that's the output. Yes?
Yes, sir.
All right, so we are looking at circuits with D flip-flops, and we are looking at these circuits. But how about the other flip-flops that we spoke about? What about the T flip-flop? Let me just throw a spanner in this book now and see what happens. Let us analyze a circuit now, a sequential circuit using a T flip-flop. Let us see how that works. Now for the T flip-flop, let's look at this circuit and let us see if we can identify, first of all, we can identify the input and we can identify the output. It's quite clear that we have 1 input and 1 output. Now, it is also clear, or it should be clear, that we have 2 state variables, A and B. Now, can we obtain equations for the equations for the T? And can we obtain the next state equation? And then can we obtain also cooking or something? So again, can we obtain, look at the 4 things in red to see if we can obtain those. And let us first start with obtaining the flip-flop input of the the T line?
Sir, T is
What
X
is it?
and B, sir, for TA.
X and B. All right.
Yes.
So you can probably write that down because we are going to need it a little later. And since we get X and B, or B and X, or BX, however you want to call it, what about the next state equation?
It's just X.
Pardon me?
Oh, next state space, sir, that is,
What about the next state equation?
oh, that is X, sir.
How do you get X?
So you only have one line going into the input, sir.
The input of what?
The second T flip-flop.
I said the next state equation.
Oh.
I'm sorry. You're giving me the state equation for both the B flip-flop and A flip-flop.
Yes, sir.
Yes.
You are correct for that. It's X going into the T. I'm saying no. What? So you are correct. So the two equations are for the A. You have, so for TA, you would have X times B, or X and B, or BX. And TB, you would have X. TB is equal to X. Is that so?
Yes, sir.
All right. Now, the other question now. What are the...
Wait, sorry, sir. Can you just repeat that? The sound break up a while ago.
Let me write it.
Sir, if you can write it sometime on the screen, because sometimes when I listening back to the audio, it's either low or sometimes with the other break up and you don't hear clearer what was said. I mean the recording.
Yeah, but I can only write so much because I have to pick my points where I write, because I can't write everything on the board. You get what I'm saying? So I have to choose where I actually write, place or the points in the presentation where I would write. So this is TA, so let me write that. And it is quite difficult to write with these mouse tools that they have. All right, and this one now is B times X. B and X. Let's say that is that. Yes? So do we agree with that?
Yes, sir.
All right, so from there now, let us see where we go from there. What about the next state equation? So those are the equations at the T inputs. In other words, the T flip-flop input equations. What about the next state equations? Pardon me? You're saying these are the next state equations? All right. Any other input? In other words, any other answer for this particular question?
Sir, I agree with him, sir.
You agree with him?
Yes, sir.
All
Sir,
right, so go ahead. Stop.
repeat that. Yeah, for blackout. Repeat that, please.
The next state equation.
Yes, sir. I was saying, sir, it was independent of. It's independent. It's dependent on the input of TA.
So you're looking at the next state equation for this one.
But yes, sir. For the top T flip flop, because depending on what the values are, you will either it would toggle the, so you get the complement of.
Where is the next state? That's the first thing you need to understand. How do you calculate the next state for T flip flop?
So the next state would be at A for TA at the flip flop.
Why would it be there? Why would it be at the output?
Why would it be at the output?
Yes. Never at the output. Next state is never at the output. Next state is always at the input.
Okay, sir.
Yes?
Yes, sir.
The present state that is at the output. So please remember that. Whenever you construct or design any sequential circuit, whatever comes out of the flip flop, that is the present state. Okay?
I'm sorry.
Go ahead, please.
Not to label the point, but how you end up getting TA equal BX?
Follow the lines on the diagram. There's an AND gate just in front of the T input on the T flip flop. Look at what signals are being ANDed together. Look at what comes out of the AND gate. See it now? Afraid of?
I'm seeing BX come out of the AND gate.
Pardon me?
Yeah, I'm seeing BX coming out of the AND gate.
Right, so I'm saying that TA is just the variable that we're saying because it's a T input of the A state variable. So this flip flop we're calling the state variable A. This state flip flop because the label here is B. We call it state variable B. And that's what we have been doing. Okay, so we're just calling that TA. Simple equation there. I could have put just BX by itself and it really shouldn't matter. So I'm saying it's the BX in the T input, the A state variable. All right.
Okay.
The other one. All right. So based on what I think Richard said it. This here really is not the it's not the next state equation. So Px is not the next state equation because this is a T flip flop. If you remember from the last class, and notice I'm making reference to the things that we did in the last class because it's very important. If you remember from the last class, the characteristic equations for the flip flops for the D flip flop, and that is what we didn't mention earlier, but I didn't mention it deliberately because I wanted to reach this point and to understand that for different flip flops, the next state equation is different for different flip flops. Now for the D flip flops, if you remember, QT plus 1, which is the next state, is always equal to T, but it's at the D input. And that was the thing for characteristic equation for the D flip flop. However, for the T flip flop, next state is always equal to T exclusive OR with the previous state or the current state. So it is really to form the next state equation for your T flip flop. You're going to have to exclusive OR, run exclusive OR calculation between the present state and at the same time T input. So that is why we work on the T input first, so that you can use it now in an exclusive OR operation along with the present state to form next state. And let me go and show what it means. So if you recall all of these things from the previous class, then this is how you would calculate the next state for all of your different flip-flops. For the next state, for the D flip-flop, whatever is at the D, it is the next state. And that is why when we started with the D flip-flop. And so when we calculated the next state at the input, then we use it as when we calculated the D input, then we use it as the next state because of the characteristic equations. But if you look at the T flip-flop, and if you remember, a T flip-flop is really a design flip-flop using we can use a D flip-flop to design all the other flip-flops. Or we can use a JK flip-flop to design the T flip-flop, just to see. So the T flip-flop can either be designed using a JK flip-flop or it can be designed using a D flip-flop. The characteristic equation for the T flip-flop is really T exclusive OR with the present state. And so that is what you need to use now in order to generate your next state logic. So let's look at so what is the next state logic? Now, if you should go ahead and do your calculations, I'm giving you a little time to do it. Remember, right here is X. Down here we have, this is just X. So let us calculate the next state for variable A. Let's do that one first. Remember, for variable A, you would have, let me write it here, or for both variables, we have TA equals dx and TB will equal to X. So for the next state equations, remember that. For the next state equations, let us see what we have. Would you calculate them for me, please, and tell me what you come up with? Let me go back to the screen before. Remember what you're working with now for the next state equation is this. Because we're dealing with T flip-flops. So the next state equation, now Q is the state in this particular equation here. So for QT plus 1, to get QT plus 1, which is the next state of the flip-flop, of the T flip-flop, by the way, we would simply XOR the T input with the present state value. Whatever is at the T input, whatever we calculate for T, we do an exclusive OR calculation with the present state value. So now let me go back to where we are calculating the next state.
So, sir, so for TA, the next state would be T, which is BX exclusive OR BX?
Yeah.
Or T exclusive OR BX?
For the next state, would it be
Yes.
T exclusive OR BX?
Yes.
No, that wouldn't be. Why?
So the present state would be, the present state for TA would be what?
The present state would be what?
For present state for
You broke up a while ago. The present state for TA, for A, or for T?
for the A variable.
Yes, we go what?
what I'm trying to find. Sir.
Just look at the diagram, it's right there. And I just said it a while ago.
Sir,
Present state is always at the output of the flip-flop. And I'm not going to say it one more time. That's the final
Sir,
time.
the next state equation for TA would be BX, X or A.
Well done. I'm so grateful that you could have come up with that answer, sir. So the next state equation would be, let's go again.
The BX, X or A.
Talking about the state variable is A. Let us say it's A. I don't need to write this because it's really supposed to be coming up. I remember properly. So it's TA exclusive or A. Do we agree?
Yes, sir.
Fine. So whatever the T input is, then you're going to do an exclusive OR calculation with that value and A. All right. What about the next state for B?
It would be X or X.
To be X,
X or B.
X or B. Thank you very much.
yes, sir.
Let me just erase this here, and then we start again. All right, so those are the two equations. So the input BX together with the present state, then that should give us the next state variable for the A input and for the A state variable, and then the next state variable for the value for this B state variable also given using that particular method. So we have two exclusive OR calculations here, and those two exclusive OR calculations would give us the different next state values. Now, what about the output value? Can you now say what the output value is?
So the output value would be the next state of the A variable and with the next state of the B variable.
Why?
Sir, BX exclusive.
Look at
BX
the diagram.
X or A, X or X, X or B.
Please look at the diagram. The output value is Y.
Y equal
A and B.
A, B. I don't know why you guys just making this thing so difficult. Remember, the next state is here. Pay attention. Next state is formulated at the input, really. Here. And because this is a T flip-flop, the next state is calculated a little bit differently from the D flip-flop. For D flip-flop, whatever is here represents the next state variable. Whatever is at the input represents the next state variable. For T flip-flop, you're going to have to take whatever is at the input and do an exclusive OR calculation. If you remember, for the T, let me see if I can redraw. Remember, a T flip-flop is like this. You use a D flip-flop, calculate a T to create a T flip-flop in this particular way.
Sure.
Anyone here can remember? And
Sure.
then let me just finish drawing this on the board. This is how a T flip-flop is created. So when you get a T value, the T that you're calculating is not really here. It's not really here, not yet. T value that you're calculating is at this point. That's the T value that you just calculated. The the characteristic equation has to come through to D, because when it comes through to D, then it can be the same thing as D. Whatever is going through to the flip-flop, and that is what the characteristic equation is. So for the T flip-flop, you have to calculate what happens here. And this is the next state, because the T flip-flop is made with D flip-flops. And that comes from the, again, from the last lecture. So this is where a T plus 1 is at the input here. That is where it is. So remember, the T value just gets you to the XOR at the input of the XOR. And so that is what happens for the T flip-flop. Okay? If you remember this, then you probably wouldn't have so much of a problem. So are we okay with this now? Now that I put this diagram on the board, I suspect you should be okay right now, or at least closer to the problem, solving the problem of identifying where your next state logic lie and where does the present state logic lie.
It's a bit clearer. What I was saying, Frida said to excuse him because his data is finished.
Okay, that's okay. So I'm saying again, and make sure we understand what is here. Now, this is how we create a T flip-flop. T flip-flop can be created using a D flip-flop or a JK flip-flop. So the exclusive OR calculation comes from the fact that the T that you're seeing at the T input there is really not at the D input. And it is only when it gets to the D input, then it becomes the characteristic equation. So the T value that you get there must be XOR, or it must be an exclusive OR calculation between the T and the present state. That is what you see happening there. And therefore, when it gets to the D input, now that is when we can use that particular equation, as we did before. That is when we can use that. Whatever we get at the D input, then that represents the characteristic equation. And so that is where this came from. How about the output equation? And we said that the output equation is, we already said that it is AB. Once you look at that, you will see AB. Output is Y, and Y is connected to A, and it is also connected to B. All right, so from here, obviously we go to the state table and so on, and let us see what is happening. So I want you now to verify, again, just to verify that the state table is actually carrying the same information as the equations that we have. So pay attention carefully and let us see what we have here. This one you have to do a little bit more calculation for the next state, because the next states are actually XOR calculations. And in particular, with the first calculation, the next state for A, you would have an ANDing to do before you actually do the XOR calculation. So you're going to have to just go through it a little slower to identify that these values are, in fact, the correct values for this particular state table, and the correct values that represent the circuit that we just looked at. So I'm giving you a minute, and then you can identify whether or not it is there. So are you okay with this?
I'm gonna finish, check everything out, sir.
All right, we have, how much time do we have left? Let's check to see how much. Oops, we have 27 minutes remaining. By my clock.
Yes, sir. Everything is okay, sir.
Yes, sir. That's it.
And again, we check the state diagram. Check also the state diagram for yourselves to see, verify that it is also giving the same information. And note now what the difference in this state diagram, the difference in this state diagram and other state diagrams that we have seen previously. And please feel free to ask questions about the state diagram.
So, sir, for this state diagram, sir, the present state and the output is represented in the same circle.
Yes. This is because the output has nothing to do with the input at all. The output is totally dependent on the present state or on the states. So if you go back to the equation, let's go back to the equation as before. You notice the output value, y is equal to a and b. Has nothing to do with x.
Okay, sir. See that, sir.
Right. So the output it achieves a value when it is in a particular state. So as I said before, verify that the state diagram are well, the state diagram and the state table are basically saying the same things. All right, so that's the T flip-flop. Now what about the JK flip-flop? How do we design with the JK flip-flop? How do we get the characteristic equations for the JK flip-flop? So again, it's the same procedure. No, same procedure, different flip-flop. Okay? So now, let us see what happens here. So can we calculate the inputs for the J and the K in the case of the JK flip-flop? And once we obtain those inputs, then can we work out what the next state equations would be? And then we also have to work out what the state table is and the state diagram. So can we reverse engineer the circuit to see what everything is before? In other words, what did we do to put this circuit together? And that is the reverse engineering. And that is how we analyze the circuit. So first of all, let us try and figure out what are the J and the K inputs for both state variables A and B. So in the case of A, state variable A, what would be the J input and what would be the K input? By the way, that's a question. I've been asking these questions since morning. What would be the J input for the state variable A?
For A,
yes.
For A it would be
Now unmuted.
B.
Yes.
And K is not XB.
And K is not XB. So let's see if we can write that down. Just scribble it down somewhere on the slide. And then we can verify it later. So for A, J input is B. That's what they said.
B. Yes, sir.
B. And
B.
K input would be
not XB.
Not X.
B.
That's it. What about the other one? For the
Hold on.
How about for the B?
Not J is not X.
So the J input is what? And the B state variable?
Not
X?
X. Yes, sir.
Fine. And what about the K?
X or A.
X or A. All right, fine. All right, so that's that. What about the next state equations now? Do you remember what the next state equation for JK flip-flop, how you calculate that? Remember calculating the next state equation. So let us calculate the next state equation for, generally, let me write it down. Generally, the next state equation is Q, call it T plus 1. And then that would be equal to J, right? And then Q prime plus A prime Q. So basically that's how you would work out the characteristic equation for your JK. Take the J values, and you simply AND it with the complemented present state value, and then you OR it with the complement of K and present state value. So it is JQ prime, okay, plus K prime times Q. In this case, if we want to write it down for the A variable, it would be JA that we just calculated, and or dot A prime, because A is the present state value. And then it would also be plus KA prime. And then we AND that with A. So let us look at the values and see what happens here. So in essence, this is the present state value here for the A flip-flop. And this is the J value for the A flip-flop, the J input. And this is the K value. But none of these values can't be used as is. We have to know, to create the next state equation, we have to now use the characteristic equation to form the next state equation for this particular JK flip-flop. And so when you work it out, you're going to end up with these values for your JK flip-flop. All right, so verify that these values are indeed correct, but we don't have much time. So I'm going to move from this, and you verify it a little later on, whenever I upload this particular presentation onto the website. So from there, again, we look at the table, and we sort out the table. The table needs verification once more. So once you verify the table, the flip-flop inputs, they are not necessary, but basically it doesn't hurt to have them there for the different JA and JK values. So it's really not, it's not a must, but it couldn't hurt, especially when we have just 4 additional columns to our table. So verify that everything works for yourselves, and from there, again, we normally go to the state diagram. And then once you go to the state diagram, you can look to see whether or not the states are represented properly, and the transitions and also the inputs and the outputs are represented properly for this particular state diagram. Now, if you look at the state diagram, there's one thing missing.
Output, sir.
Everybody tell me what is missing.
Output.
Yes. And what would be the output? Where would you actually put the output? So you have seen where we can put the output two places, either on the transition arc or in the state bubble. Where would you put
in a state bubble, sir.
Okay, why? Why would you put it there?
Sir, because it's not affected by the input.
Okay.
Or the input.
All right, fine. So the output really and truly don't have anything to do with the input. It's really just a handing of the two state variables. And so in these cases, you would, let us say for state S0, what would be the output at that state? By the way, that's a question. What would be the output at that state, S0?
Zero, sir.
Hmm?
0.
All right, what would be the output at S3?
Zero, sir.
How would you get 0 in that case? I really don't know.
One.
Huh?
1.
All right, how are you calculating the output? Because it's so uncertain.
If they said the output was the ending of the two states, so.
Okay, fine. So if we go back again, we would view that the output, see here, right here, output is ending of the two states. Yes?
Okay, sir.
I don't know if this is the same. Let me just check to see if it's not the same. All right, so the output is the ending of the two states, and that's basically what we got. All right, so let us move to a more general presentation now of sequential circuits. Now, as I said before, there are only two types of clocked sequential circuits that we design. One is a Mealy machine, one that we call a Mealy machine, and then the other one is a Moore machine. The difference between the two can be seen in the diagram displayed. The Moore machine, if you notice with the Moore machine, the output depends only upon the state itself, the present state. Can you all see that? So the output, note this is a combinational circuit for the output. What goes in? Present state. That is basically what goes in. So the output is dependent upon the present state. If you look to the Mealy machine though, you recognize that the output not only depends on the present state, is here. I don't want to put it here, let me put it on top of here. That's the present state, but also it depends on the input. So the output depends on the present state and the input with the Mealy machine. While with the Moore machine, the output depends only on the present states. Now there are some advantages and disadvantages of both. Usually, the Moore machine you end up with more states, more state variables, at least one more. And for the Mealy machine, you end up with situations where you can have false outputs, or what we call jitters or in the jitters in the output and glitches within the output, stuff like that. So let us look at the Mealy machine first and foremost, and let us just look at some of the characteristics, some of the things that you can happen with a Mealy machine. Now, as I said before, the outputs, they are a function of the present state and the inputs. Note again that the output is not synchronized with the clock. That means the clock don't have anything to do with the output. You pretty much get the input from the present state and the input, the external input. So at any point that external input changes, it can generate a change in the output of your Mealy machine. And that is usually what causes the glitches when an input change within the clock cycle or just after the clock edge has been, just after the clock edge has been triggered. Whenever the input changes, it usually give out at the output what we call false output or glitches. So that's one of the things that is usually you have to be aware of when you're creating Mealy machines. All right, but eventually the output is corrected, and the output is always correct just before the next clock edge, or just before the clock edge itself. For Mealy design, so this is what we were looking at earlier. When we have Mealy designs, the output is now, if you look at the transitions, the outputs and the input are basically on the arc. So this is for Mealy machines. When you have outputs and inputs on the arc, when they are listed on the arc, then we are really representing a Mealy machine. In that, we are saying that the transitions in the output values depend on the input and the state, the present state. So that is basically what we're saying when that occurs. So if you notice right here, the output and the input are on the arc itself, and that is typical for a Mealy machine state diagram. Now you could basically trace this particular Mealy state diagram, and if you want to learn how to trace the diagram, it's really a similar thing to plotting timing diagrams and identify what happens at each clock cycle. Now, as usual, as before, if you remember, we said that in the initial stages of once you turn on the flip-flop, they really don't know what values are there. So therefore, you end up with these two question marks here, indicating that we are not sure what is in the flip-flop. All right, so at those stages. But if you look at the diagram itself, when you get a 0 at the input, it actually forces the flip-flop into 0-0 state. Because if you notice, it doesn't matter where you are, wherever you are situated here, once you get a 0, it comes right back to 0-0 state. So if you could look at it, just look at it, notice that 0-0 state, if you're in this state and you get a 0 for your input, that's a 0. If you are in that state, if you are in state 1-1, you get a 0 on the input. If you are in state 0-1, you get a 0 on the input. It goes back to, all of them are heading back to state 0-0. So once you get a 0, once a 0 is indicated on the input at the initial stage, it forces the state machine into the 0-0 state. And so that is what happens. So if you look at what happens here, so gets a 0, next transition, on the next transition, it forces it into the 0-0 state. 0 for A, 0 for B. That's the state. And the output at that point would be 0. Now, please to go through this tracing of the Mealy state diagram. We don't necessarily have to trace it. We could use timing diagrams, but go through it just to verify that what happens here is really what is being represented by the state diagram. When you get a 1 on the next clock edge, it changes to 0, 1. So at the previous state, the present state is 0, 0. If I get a 1 at the present state, where does it go to? It goes to 0, 1. Let us look on the diagram to see if that is the case. And yes, it is. Once you get a 1 on the input, you go to 0, 1. State 0, 1 here. So as I said before, verify that this is okay. And then you will understand exactly what is happening then in that particular.
Just verify it, sir.
Pardon me?
I just verified it.
All right, fine. And that is good. This is basically the same thing we are showing on the diagram. But now we are looking at it in a graphical manner. We're looking at it by signal timing diagrams. And therefore, if you look at what we have here, there's just one thing I want to point out to you, which is the false output occurring for this particular Mealy diagram. False output, if you notice, this, by the way, is a trailing edge triggered circuit. So it basically responds, or it's triggered on the trailing edge. So we're looking for all the trailing edges in the clock cycle, or in each clock cycle. These are the trailing edges in the clock cycle. Now, if you look at where the false output occurs, it occurs just after the clock edge and just before the input signal changes. And that is what where the false output usually occur. Because of the fact that the input, with the Mealy diagram or the Mealy state machine or sequential circuits, with the Mealy, what happens is that because the output is dependent not only on the state, it is also dependent on the input. It responds to changes within the input. And therefore, if the input changes just after the clock edge change, or just after the clock edge has arrived, then it will spike the output. Not in all cases the output will be spiked, but depending on what the input changes to and changes from, then it will trigger a response in the output circuit, which is a false output. And you eventually, if you get back the correct value, eventually it will come back down or go up in the case where it is a false 0, or in this case we get a false 1. So it will basically level out to the correct value. But just after the clock edge and just before the signal changes, you will get a false value for Mealy circuits. And so this is one of the drawbacks with a Mealy circuit. But then, as I said before, it basically levels out for the clock cycle, and just before, and we are certain that just before the clock edge, the correct value for the output is available. False outputs don't occur in more machines, and obviously you could see why it doesn't occur. These glitches don't occur because the more machine, the output really is dependent upon the state only. So it doesn't matter what the input does at that particular point in time. Once the state comes through from the clock, then that is the only time that the output will be changed, because it basically gets its input values from the clocked state register, and then every time the edge is arrived at in the state register in turn changes the output, and then the output circuit for the Moore machine also changes the output. And therefore, we also say that the Moore machine, the outputs are synchronized with the clock. So it means that every change in the clock really will generate a change in the output. And again, we say that we have no glitches, and that is one of the nicest things to have, no glitches. Irrespective of what the Moore machine does though, there's we don't exclude the Mealy machine totally, because as I said before, there are situations in which the Mealy machine are very useful. And so you will find that our designs later on will be a combination of Moore and Mealy machines. So they use both Moore and Mealy machines in the design, and therefore you should be able to spot all the different advantages and disadvantages when using either. Finally, if you look at the trace diagram for your Moore, and if you look at the state diagram for your Moore, you would notice now that this is the one where you actually include the output as a part of the state bubble. Why? Again, because the output simply is dependent only upon the state itself. Doesn't have anything to do with the input. Okay? All right, so verify for the final timing diagram. I want you to verify that this works in the same way that all the others worked before. You need to verify them for yourselves. I will simply put up these slides, not right now because I have another lecture right after this one. So I will put up these slides a little later on. However, when they go up, it is your duty to verify all the things that we spoke about within the lecture. And so this is basically me saying goodbye. And if you have any questions at this point, I'm taking the questions right now.
Sure.
Go ahead, please.
Yes. So will the last class be next week?
By my calculation, I think next week. Yes, next week. I have next week to be the final week. Yes.
Okay, sir.
Remember, we have tests. Oh, I tell you what. Remember, we have 2 tests to do, and therefore we're going to have a test coming this Sunday. Yes. We have to use the weekends. So please bear in mind, let me just speak to you directly. It's really a very good thing that you reminded me about. So let me put it out from now. Yes, we have 2 tests left to do, and therefore we're going to have to do one next week Sunday and then the following Sunday. 2 tests in addition to your final exam. So we have 3 tests remaining. We also have, well, I could, if we can do 2 labs, we can do 2 labs instead of 2 tests. We can do 1 test and the final exam. And we can do 2 labs. All right, I will give you 2 labs. You'll get 1 this week and then 1 next week. You'll get 1 tomorrow to turn in next week, and then you'll get another 1 next week, turn in the following week. And you will also get another test. If I give you 2 labs, I'll give you another test.
2 lab, 1 test.
So it's 2 lab, 1 test. You voting on that?
Yes, sir. That better. To me.
For you?
Yes.
All right. So you're getting 1 test plus 1 final exam. So that's 2 tests for the remainder of the semester, and you have 2 labs. Okay? We definitely need the 2 labs, and that is why I'm going this route, because the previous labs that you did, oh my goodness, leave much to be desired. So hopefully you met the grade this time around with the 2 labs that we're going to do.
Sir, I'm still not seeing any grades for the previous labs.
sir.
We really don't want to see those guys, yeah?
Okay.
That is why I'm trying to give you at least two more labs.
Sir, we don't know the mistakes we made in either the lab or the report to.
The report is the lab per se. And the report, I basically gave you an example of how. So if you compare the report, your report with my example, then you would see all the mistakes that you have made. And that was why I gave it to you, because I can't take the time out to go through and show you everything. So that is why I made the example report so that, and I basically left it online so that you can review it and see where you have made mistakes. No, I didn't give you every single thing inside that report, but I gave you a method and an outline as to how you present your work or your circuits. So once you compare that with the ones that you have, then you should see all the mistakes.
Okay, sir.
So these upcoming labs will be from where to? From which lab to?
We'll be doing the labs will be in system very long. So in other words, you'll be writing codes for these labs. Now so you have to get your house in order with respect to the Quartus Prime tool. Okay?
Okay, sir.
All right. All right, so any more questions? If you have no more questions, then I will adjourn. All those in favor?
Aye.
All right, the ayes have it. All right, see you next week. Well, see you tomorrow. I will be here tomorrow morning. So bye-bye until tomorrow.